Okay. All right. Well, we're very happy to have Csaki here today from Cornell University. Csaba got his PhD at MIT, moved to, I think, Los Alamos, and is now endowed chair at Cornell University. And Csaba is a world expert on BSM physics, especially with a little bit more pheno and formal flavor to it. So Csaba's going to tell us about understanding QCD dynamics from supersymmetry. So without further ado, please go ahead.
Thanks very much. It's great to be back. I'm going to be talking about the work I was doing over the last few years with this set of people. So Rafael, I guess probably everybody knows. Rick and Tuhin are actually at the Tata Institute. I was at a sabbatical there, so that's when we started working on this. Eric Kuklik, I guess many of you may know him. He's now professor at Hebrew University, actually on sabbatical at Cornell. Now Max was a former postdoc at Cornell, and Tabuk is a Cornell postdoc right now. And it actually builds on the previous work that we did together with Hitoshi. He kind of restarted this whole area of trying to use EMSB for QCD-like dynamics. Andrew used to be my student at Cornell, and Hopefrey is a professor in Hebrew University also. All right, so at the beginning, I will try to explain to you how we are trying to use supersymmetric theories to try to learn a little bit about QCD-like dynamics. And I will also explain to you what I mean by QCD-like dynamics. So these will be theories that in many respects have similar properties as actual QCD, but they descend from a supersymmetric theory. So you will actually be able to calculate many things exactly, but it will also mean that of course, they are not really truly the QCD dynamics. So I mean, we will learn some interesting dynamics. I'm not claiming that it means that we are solving QCD, but there are several things that, at least to me, were sort of hard to understand within ordinary QCD, and you can get a pretty clean answer to those questions at least in these models. So the examples that I will be focusing on is looking at the eta prime potential, and in particular, if you also had an axion in the theory, then what would be, how would the axion mass actually be generated in this theory? Another interesting direction is sort of understanding spontaneous CP violation in QCD. So that's maybe a little more esoteric thing, but I guess I will explain why that's something that is sort of an interesting dynamical question that exists in ordinary QCD. People have guesses what happens there, and here in these theories you can just go ahead and calculate it. And then this is what is work in progress right now. I think it's pretty interesting also. So in these theories we will actually be able to just derive the chiral Lagrangian and answer the kind of questions that people are always wondering within QCD. For example, how large is the dynamically generated up quark mass, and in particular, could we actually, is it big enough such that the underlying up quark mass could possibly be zero or not? So I think at least within these theories, we will have some concrete answers to those questions.
What does the acronym AMSB stand for?
I will explain. Anomaly mediated supersymmetry breaking. So it's a particular way of going from a supersymmetric version of QCD to a theory that doesn't have supersymmetry. I will explain why that's sort of the preferred version of trying to do this this particular exercise. Okay, so again, I will try to explain again, what the basic construction is, why we are trying to do this. So of course, the nice thing about supersymmetry is that it gives very powerful constraints on strongly coupled theories. Of course, at some point they thought maybe it's actually a theory beyond the standard model of the TeV scale. Now it becomes less and less likely, but it doesn't mean nothing about supersymmetry could be interesting to physicists. And again, the direction that's probably still the most exciting about people who care somewhat about supersymmetry is to just use it as a laboratory for understanding strong dynamics. And so when I was a grad student, there was a big activity in trying to understand the phase structure of the supersymmetric version of QCD. And that was actually led by Seiberg and also by Ken Trilligator and a bunch of other people. Many of them were at Rutgers at the time, etc. And by 1994, they essentially were able to nail down the phase structure of the supersymmetric version of QCD. They were using particular kind of techniques that some of them are specific to supersymmetry, some of them are general techniques for analyzing stronger decoupled theories. So holomorphy is something that is, of course, very specific to supersymmetry, and the fact that, you know, part of the Lagrangian has to obey holomorphy, so the superpotential, that gave a big boost to this exercise. And then there are additional techniques that, you know, were used. For example, 't Hooft anomaly matching, just doing explicit instanton calculations, which in some cases turns out to be in the regime very reliable. Of course, you know, doing an instanton calculation is not always possible, just because, you know, they themselves may be strongly coupled, but there were particular cases where you could actually do a reliable calculation in these cases. And also, you know, you were able to connect various theories by integrating out flavor or Hicksing the theory and seeing that you get sort of a consistent web of these exact results. Okay, so what happened was that that you got essentially sort of, you know, this picture. This is what emerged from all this activity in the 90s. So
Is F the number of fermions and N is the.
Yeah, so F is
Right.
the number of flavors.
Okay.
Yeah, so this is, let me see if I wrote down the theory here. Okay, let me show this one first. Yes. So this is an N equals 1 supersymmetric SUN gauge theory with F flavors. Yes. So the flavors are in chiral superfields. Okay, so they contain both the quark and the squark. Yes, and then, you know, this is N equals 1. So for a gauge boson, there's also a gaugino superpartner assumed here. Okay, and so the kind of structure that you got was this phase diagram that tells you essentially what is the dynamics, what is the low energy phase of the supersymmetric version of QCD, as you, let's say, if you hold the number of colors fixed and if you change the number of flavors. Okay, so this would be like the pure super young Mills, and I will explain this in a little more in a moment. Yes, so in that theory, you know, there's actually a dynamical effect that is called gaugino condensation happening. No, when you start increasing the number of flavors from 0 to non-zero, but it's not too large, so if the number of flavors is less than the number of colors, you get what is called an Affleck-Dine-Seiberg superpotential. So this is the other ADS, is not the anti-de Sitter. So this is Affleck-Dine-Seiberg. I will explain also what this is. And you know, as you increase the number of flavors, you know, there are increasingly exotic kind of phases showing up in this theory. So for example, you know, when the number of flavors equals the number of colors or equals the number of colors plus 1, there's some very special cases happening. Some of it is a little bit like QCD. There is some particular form of global symmetry breaking that is happening. But if you increase the number of flavors by 1 more, then actually there's no global symmetry breaking. You know, there is some weird thing that is called S confinement, where you know there's just a smooth vacuum without chiral symmetry breaking, and all the 't Hooft anomalies are actually matched up, so you can identify what the massless degrees of freedom are, which contain massless fermions, very unlike QCD. Okay, and then, you know, there are increasingly more and more exotic things. Free magnetic phase, where actually, you know, you start out with a QCD-like theory based on a given gauge group, and in the IR you get another gauge theory. Yes, which is now weakly coupled based on another gauge group and another matter content. So again, so all these weird things, you know, they are really beautiful, and you know, but that's not the main point of this particular talk. So this is what is called Seiberg duality here, and you know that some people may know about this. So again, so this is the theory that we are studying. Sometimes we call the fundamentals Q and Q bar. Sometimes people call it phi and phi bar. So I wrote both of these, and the important thing is that at low energies in the supersymmetric theories, the theory is described in terms of what are called mesons and baryons, and they are not quite exactly the same thing as the usual mesons and baryons of ordinary QCD. Yes? because this is a QQ bar supersymmetric bound state, yes. So for example, the scalar component of this meson field, yes, is made out of the scalar components of the quarks, yes. So in some sense, it's similar to the ordinary meson, yes, but actually, if you look at what would be the scalar of this, that would be made out of is the bound state of two quarks, not the two, not the quark, not the fermionic part like you see in ordinary QCD, etc. So you have to, be a little bit careful with understanding what this means. Okay, let me try to explain at least a few of these dynamical results that have been obtained. And again, I don't want to go into a lot of detail, but let's see, for example, for the case of no matter, so that's called the pure super Yang-Mills theory. Yes, it's just an SUN supersymmetric gauge theory. So all you have is gauge bosons and gauginos, no matter fields. Yes, so there's no continuous flavor symmetry in this case. Now it turns out that there is a discrete flavor symmetry that is left unbroken, that is essentially rotating the phases of the gauginos. Okay, so there's a Z2n discrete gauge symmetry. And that actually played an important role in terms of identifying, what the right dynamical picture of this theory is. Yes, and again, I'm not going to go into detail of where this is coming from. Just give you the facts. Yes, that the right dynamics that is describing this theory is actually one based on gaugino condensation. So there will be a condensate in the vacuum that doesn't break supersymmetry. Yes, it doesn't break. So it's a supersymmetric ground state. It doesn't break supersymmetry, but there are n different values for this gaugino condensate. And those n different values is going to break this discrete Z2n symmetry down to Z2. Okay. And so this is supposed to be a truly confining theory, meaning that if you take two test charges in the fundamental, yes, this doesn't have dynamical flavor, yes, but you can consider external test charges, and there would be a linear potential between those external test charges. So that would be, the description of what happens down here. Yes. Now we can go to one higher case. So that's what is called the Affleck-Dine-Seiberg superpotential. So now this is another interesting and weird example. Yes. So this actually was identified much earlier. So that's 10 years earlier, 1984, when these people found the description of this theory. It turns out that in this case, there is a dynamically generated non-perturbative superpotential in the theory. Okay, so, and the form of it is pretty weird. It has this 1 over the determinant of this meson matrix showing up, and it's taken to some weird fractional power. And what happens is that really this is telling you that the theory doesn't want to live at the origin, where the meson field has no vacuum expectation value, but the vacuum is actually going to be running to large values of this M. So we would call this a runaway vacuum. Of course, it can be stabilized. If you add another quark mass to the theory, then the theory will just have a normal spontaneously broken vacuum at some finite value of M. Okay. And the interesting thing is, again, the reason why people were pretty sure, already in 1984 that this is the right thing is that for one particular case, when F is equal to n-1, this was one of the very first examples where you could actually perform a truly reliable instanton calculation. And it's not super hard to at least outline, what happens there. Yes. So there's some sort of an instanton, yes, and you can have to count the fermionic zero modes in those instantons. So it's a supersymmetric theory. So you have gaugino zero modes and you have also quark zero modes. So each instanton is going to have one particular, one of the flavors, flavor zero modes sticking out. And then for the gauginos, you actually have 2n. Okay, so for SUN, you have 2n gaugino zero modes sticking out. So you have to close up all of these legs because you're trying to find a contribution to the superpotential. One piece of that could be, either a fermion mass or a contribution to the potential. You can close them up with all the couplings that are present in the theory, and then you can essentially perform the integral over the instanton size and show that the final result is actually a holomorphic object that can be derived from the superpotential. And so this is actually something that has been done. And as I said, it's to my knowledge, one of the first examples where a truly reliable instanton calculation has been performed. Why is it truly reliable? Yes, because for f equals n-1, the gauge group is completely broken. Yes, so you can go to a point where the meson picks up a large expectation value. Yes, that breaks the gauge symmetry before the gauge symmetry could actually become strongly coupled. Okay, so that means that you don't have the usual problem of the IR divergence of the instanton integral. Yes, because this meson web actually provides an IR cutoff for your instanton size integral. Yes, so you can actually reliably calculate it, and you can estimate it if you are a lazy person like me, or if you're a serious person. People have actually calculated these coefficients in this instanton integral. Okay, so that's how people were able to identify this. And again, once a term like this is present, then what will happen is that the gauge group is actually going to be broken, at least an f equals n-1 completely. If f is less than n-1, then it's going to be partially broken. But then, once every flavor got an expectation value, then essentially, the price for making those gauge, for breaking those gauge symmetries is that it is going to eat all the flavors. Yes, and then you are back for the remaining theory. You're back to the previous example. There you have a pure super Young-Mills with some unbroken SU n-f gauge group. And there what happens is gaugino condensation. And that gaugino condensate can actually be identified with this Affleck-Dine-Seiberg superpotential. Okay, so again, there's this intricate web of consistency checks, and you can go ahead and again, show what happens in each of these cases. I'm not going to go through all of this because then I'm going to spend all the lecture on explaining stuff from 1994, and that's not what I'm trying to do. Yes, but what I'm trying to say is that you have all of this interesting and pretty exotic kind of stuff happening, and that was a lot of fun to try to figure out what happens. But of course, one thing that you should notice is that this doesn't look at all like the phase structure of ordinary QCD. Yes, ordinary QCD doesn't have most of these things. Yes, we know what happens in ordinary QCD. You have just essentially confinement with SUF cross SUF cross SUF broken to the diagonal. So you have chiral symmetry breaking with a particular pattern. Yes, the SUF left cross SUF right is broken to the diagonal SUF. Okay, there's another possible phase in QCD. And that one is when the number of flavors is becoming really large. Yes, then there could be a conformal phase. So that's something that the lattice people do see. We don't exactly know where that boundary between the usual QCD, the normal QCD-like phase where you have just the chiral quark condensates breaking the chiral symmetry, and there you have a conformal phase. People think it could be as high as 3n, though I was talking to lattice people. Some people think it's a little lower than that. Anyway, so there is somewhere boundary, yes, and it goes from the normal QCD-like confining theory down to up to a conformal phase, but you don't have any of this weird stuff. Yes, so you do have the analog of the conformal phase in the supersymmetric theory, but you have all this other weird stuff happening here that doesn't seem to have a true analog of within QCD. Okay, so what you would like to see is, of course, you would like to somehow use these exact results in supersymmetry and connect them to non-supersymmetric theories. And of course, we were absolutely not the first people who tried to do this. Yes, as soon as Seiberg came out with his results, and the people around that, people have tried to break supersymmetry and see what exactly the implications are for non-supersymmetric theories. So there were all these papers from the mid-90s, and then there was another really nice one by Xinxie Cheng and Yael Shadmi that kind of restarted this activity. And then it goes all the way into Zohar and people so it's I don't want to claim that we are the first, and absolutely not. There's a big literature there, yes, and they were increasingly more systematic. The first one was pretty random. And, I think the idea to do this was nice, but, they haven't really gained much understanding, but of course, by the time you get here, there are many interesting results. However, the one thing I would like to say is that there was not really a clear pattern of what the actual phase structure of these theories are until relatively recently. So it was Hitoshi Murayama who sort of suggested that we should get back to these supersymmetric theories and use a particular form of supersymmetry breaking that is actually pretty easy to translate into, what the effect of that type of supersymmetry breaking is going to be, even though the theory is strongly coupled. So that's, of course, the hard problem, yes? That you say that you start out with some supersymmetric gauge theory, you add supersymmetry breaking to it in the UV, you know what the theory is, but then the question is, how do you map that supersymmetry breaking over through the strong dynamics? Yes, that's always the big question, yes? And so what Hitoshi was sort of pointing out, and I think that's his main contribution, that if you use anomaly mediation, then actually, the mapping of supersymmetry breaking through the strong dynamics is going to be pretty simple. Okay, so you will have a controlled way of being able to explain, what the exact results in the presence of supersymmetry breaking are going to be in those theories, as long as supersymmetry breaking is small. Okay, so just to give you a little history, so anomaly-mediated supersymmetry breaking was invented originally back in 1998 by Randall and Sundrum, and some people call that the RS0 paper, and also I guess another paper that was Hitoshi, Janjibice, Ratazzi, and Marcus, I guess, yes. And they were actually thinking of this anomaly mediation as a particular true theory of the TeV scale. So they were trying to devise a pattern of supersymmetry breaking parameters that could be a realistic extension of the standard model. So that's how it was originally devised. Now, what I want to say is that, of course, we know that that's not what is happening, yes, at the LHC. So we are not trying to go through that route. The only reason why we are coming back to this AMSD is because this will allow us, again, to study the phases of strongly coupled theories, and we are not thinking of this as an actual DSM model. Okay, so now let me explain what the assumption of this anomaly-mediated supersymmetry breaking is. So the assumption is here that there's no direct interaction between there's a sector that breaks supersymmetry, but there's no direct interaction between the SUSY breaking sector and the matter sector, the visible sector that we are observing. Okay, and it's purely mediated by supergravity. So that was what anomaly mediation was the originally devised as. And again, I said it was Lisa and Raman, and then John, Marcus, Hitoshi, and Ricardo. I think they were essentially back to back. And of course, there's a separate big literature on anomaly mediated supersymmetry breaking. So again, there's not really much new for me to add here. Again, there's the assumption that the matter sector is sequestered from the SUSY breaking sector, and the only source of supersymmetry breaking that you see here is through supergravity. Okay. Now it turns out that there's a really simple way to translate that into a simple recipe for how anomaly mediation is actually going to be affecting our visible sector. And that one was actually formulated by Pomarol and Ratazzi a year later. And so that's the formulation that I'm going to be using, because what they realize is that due to this sequestering, essentially, there's a simple way of finding all the effects of anomaly mediation via the introduction of what is called a compensator, a conformal compensator or a varied compensator, yes, which is essentially a chiral superfield that you can think of as a spurion that has expectation value in its scalar component is just 1. This is essentially what is setting the Planck scale, but you can just normalize it to be 1. But then in its F component is going to have the supersymmetry breaking parameter little m. So little m, I will always denote by the SUSY breaking parameter. So this is what is breaking supersymmetry here. Okay. And the effects of supersymmetry breaking will show up through this conformal compensator, yes, and essentially it is going to always couple to whatever the dimensions of the particular objects are. Yeah, so for example, the superpotential is dimension 3, so there will be a phi cube showing up in the superpotential. The Kähler potential is dimension 2, yes, it usually starts as Q dagger Q, yes, so that is going to have a phi star phi showing up. Yeah, so that's the simple way of seeing what the effect of anomaly mediation is on a particular theory. And
this is essentially the flat limit of the superconductor.
Exactly, right. And what you can see is that, of course, if the matter sector is conformal, yes, if the matter sector is completely scale invariant and conformal, then this phi compensator can be completely scaled out of the theory, yes. So for example, if you have only a cubic superpotential, at least at the classical level, yes, and a normal canonical Kähler potential, yes, you can just go ahead and rescale the fields, yes, and reabsorb this compensator into the definition of your chiral superfields, and it will completely remove it from the theory. Yes? So that means that if the theory is conformal, it will actually not see any of supersymmetry breaking. Yes, so that's actually very nice, yes, which tells you that the breaking of supersymmetry will be tied to the breakings of conformality. And so essentially all you need to do is identify all the sources of conformality breaking in your effective theory, and that will completely determine for you what the effects of supersymmetry breaking are. Yeah, so the reason why this EMSB is particularly useful for playing this game is because, again, it's UV insensitive. Once I determine for you a specific effective theory, you just go through this recipe of finding all the violations of conformality. Wherever you find the violation of conformality, you're going to get some sort of supersymmetry breaking that you can just go ahead and identify. Yeah, so for example, of course, you can have 3-level violations of conformality. Yeah, so will go through the superpotential or the Kähler potential, but there's also breaking of conformality through the RGE running. So whenever you have an RGE running, you can also identify what the effect of this particular form, this AMSB, is going to be on the theory. So for example, there will be contributions to the scalar masses that are proportional to the normal beta functions. Yes, and this is of course why originally people love this AMSB so much for an actual MSSM, yes, because you got the Gugino masses that were proportional to beta functions, and that was a beautiful, kind of prediction. And it also seemed to make sense in terms of, what kind of spectrum you were expecting phenomenologically for the theory. Also, the scalar masses, they were proportional to anomalous dimensions. So that was also beautiful because then, the flavor problem would be solved in that case. So essentially, everywhere where you see some running, yes, you would get you would get an additional contribution to the soft breaking terms. Now, in particular, if you take SUSY QCD, yes, and forget about trying to use this for an MSSM or anything, just take the supersymmetric version of QCD. What would be the effect of anomaly mediation at the high energies? Yes, if I didn't add the superpotential, I just have SUN with F flavors at high energies. Yes, well, you will get a Gugino mass that is coming due to the beta function of the theory, and you will also have quark masses, and you can go ahead and identify what the quark masses are from all these anomalous dimensions. And what is really beautiful is that if you check, what is the sign of the quark masses, it depends exactly on this combination, 3 times the number of colors minus the number of flavors. Sometimes I call it N and F, sorry, sometimes I call it NC and NF, yes.
Sorry, this gamma dot means derivative of gamma with
respect to mu, yes. So you can go ahead and calculate this combination, and you identify this to be exactly the borderline between the theory being asymptotically free and not asymptotically free. For supersymmetric theories, the 3NC minus NF, when NF is equal to 3NC, that's when the theory becomes asymptotically non-free. So as long as the theory is asymptotically free, we're going to get positive spark masses. Okay. And that's of course great because it tells you that in the UV, just adding AMSB to the theory is going to essentially give you a gluino mass and is going to give you positive spark mass squares. Yes. So it will start lifting all the particles that you don't want to have present in the non-supersymmetric version of QCD. Yes. You're starting to split away the squarks and the gluinos from the usual quarks and gluons of QCD. Yeah? So from that point of view, this is a good UV boundary condition for you to consider the non-supersymmetric version of QCD. Okay, so again, it produces the same thing: positive spark masses and Gugino mass. Okay, it's exactly the right spectrum. Okay, so this exactly gives you the perfect UV boundary condition that you would like for a non-supersymmetric version of QCD. Okay.
Does that relationship hold at higher order? Like if the 3n minus 3nc minus nf is 0?
Well, it's a one loop result. Yes, there will be higher loop corrections.
Do they still have that factor?
But again, assuming of course, how large these couplings are. Yes, it's a two loop versus one loop. Of course, the theory does become strongly coupled. Yes. And then the question is what happens? Yeah. That's exactly the kind of thing that we are trying to ask. Yes, we start with this boundary condition in the UV and then try to see, okay, what happens in the IR? Yes.
Right. But you also were looking at the phase diagram when like n equals 3 and c or nf or f equals 3n, right?
Well, but not above it.
Not above, but
because then it's not asymptotically free. So the theory is not strongly coupled. So it's easy.
Okay,
Yes. So IR free theories.
I see. You can do it.
Even I can do. Yes.
Sorry, what's this CI in the very bottom?
So that's Casimir.
That's just a Casimir, okay.
Yeah, it's a group theory. I think
Yeah,
it's the
okay.
quadratic Casimir.
And so will you also explain why this is better than just soft SUSY breaking?
Again, so this is a specific form of soft SUSY breaking. Yes. The point is that on this one, because I know how to, so in the UV, of course, it doesn't matter. You can just say, I just add any soft breaking. Yes. The question is, what does it map? How does it run down to the IR when the theory becomes strongly coupled? Yes. And then because I know that the effect is that this comes from AMSB, I can identify in the IR what the soft breaking terms are going to be just by applying AMSB to that effective theory. Yes. So the reason why this is, I think, somewhat better than just adding a random soft breaking is because I can sort of map through the effect of the soft breakings through the strong dynamics. Okay. And if you have other methods of doing that, then this is just one of many. Yes. But this always is going to allow you, because again, what you're going to say is that, okay, so I'm going to show you in a moment. Yeah. So I have an effective theory, and I'm just going to now check in that effective theory, what are the sources of conformality breaking? And, then I will see what the sources of supersymmetry breaking are in that effective theory. Yes. And those are supposed to be what the effect of the soft breaking is, without really having to do a full mapping of what happens to the running and after confinement. So that's the only advantage. Yes. If you are able to do it for a generic soft breaking parameter, then there, this is just a specific form where you can do this easily, I would say. And so it's UV independent, yes. So it doesn't depend on any other UV completion story, and also happens to be sort of within the right regime of boundary conditions that I'm interested in. So all of this together is what I would say why this, that's why we are thinking about this particular form. Yes, but again, if people are technically more astute, and they can do a generic soft breaking, there's nothing wrong with that. Yes. It's just that, I can do this easily, and I can essentially get all the information that I'm interested in about QCD by looking at this particular kind of example. Okay, very good. So I think I got the points through here. Yes. So Okay, so then, so let's try to apply this and show you one particular interesting surprise that again, this is what Hitoshi, was pointing out in 21. Yes, so you start out with the AMSB. Yes, and now if you go ahead and look at the formula that tells you how what the effect of AMSB is going to be on the low energy effective theory, well, there will be a piece that is going to be related to the superpotential, but this is now a term in the scalar potential. So this is, you see, this is a soft breaking term that is coming from the superpotential. Soft breaking because proportional to m, yes, but it's related to how non-conformal is the superpotential. If W was just phi cubed, this would be vanishing, yes, by construction. Yes, but if W is not equal to phi cubed, yes, then there will be an additional contribution to the scalar potential from supersymmetry breaking and this original superpotential in the theory. Okay, so, and we have a general expression for this again, the general form doesn't matter. Yes. So now that you, for example, you can apply this to the weird Affleck-Dine-Seiberg superpotential that I have explained to you. Yes, so that's now a superpotential that's proportional to 1 over that m. So it's definitely not a conformal, not a dimension 3 superpotential. Yes. So now this is actually going to induce for you an additional term in the scalar potential. Okay. So the way we looked at what the effect of this is, we parameterized the VAV of the quarks through this diagonal parametrization. Yeah, so there's the single parameter phi here, and you see it's going to give you an additional term in the scalar potential that goes with another power of the essentially this is this is some power of determinant m. Yes, and it has an additional minus sign. Yes, and the coefficient is important because it's the same coefficient. Yes, that happens to be positive for asymptotically free theories. So what happens is that there will be this additional term, and this actually is going to stabilize the minimum of the runaway potential. So this is actually going to generate a QCD-like vacuum. The SUF plus SUF is broken to the diagonal. Yes, as soon as you add a little bit of supersymmetry breaking to the theory. Okay, and again, this is a non-perturbative effect. Yes, it's non-perturbative because you have this dynamical scale in the numerator here. Yes, involves supersymmetry breaking. You see, supersymmetry breaking is going to 0, then it goes to 0, and AMSB allows us to pin down this term. Yes. Of course, it's formally a 3-level term the way we calculate it, but it also involves a non-perturbative effect. Yes, and the nice thing is that this is actually going to stabilize the Affleck-Dine-Seiberg superpotential. So what we had in the theory without SUSY breaking, we had this runaway vacuum. Yes, where the vacuum is at infinity. Now I turn on just a little bit of supersymmetry breaking. Yes, the minimum is going to be sitting at some finite value, and the symmetry breaking pattern is going to be SUF plus SUF, SUF left plus SUF right broken to the diagonal, just like in ordinary QCD. Okay, so this is what I would call a QCD-like vacuum for the theory. And the really nice thing that again that what we are finding is that as soon as I turn on a little bit of SUSY breaking, you go away from this really weird vacuum to one that looks very much like the QCD vacuum. Okay. It could also be in principle continuously connected to actual QCD if you were to take this limit. Yes. Now, this limit I'm not allowed to take. Yes, because this limit is saying that the SUSY breaking is much bigger than the dynamical scale of the theory. Yes. So I'm really losing any control over my theory that I assume. But every now and then, you close your eyes and see, what would happen if I really, really pushed? Would it make any sense? Okay, very good. So what we did also with Hitoshi and others, with Osprey and Andrew Gomes, is we actually calculated, now all the vacua of the Seiberg-like theory with AMSB added on. Okay. Now the real surprise is that we find that all of them essentially are going to be QCD-like, because there are some theories where not everything is calculable. there are some theories where, you know, there seems to be some vacua that are run away, but this QCD-like local vacua will always emerge right away as soon as you add a little bit of supersymmetry breaking. Okay, so that to me is already pretty nice, yes. And this I haven't seen from anybody else being pointed out, that, you know, as soon as you add a little bit of SUSY breaking, essentially all of these weird phases are going to disappear. Yes, and you know, it's going to look like the kind of theories that you're interested in. And so that's very nice. Okay, so now I would like to go and try to take some of these particular QCD-like vacua and shed light on some of the effects in QCD that I personally at least always had a hard time understanding, you know, how does that truly happen? And so one of the things is, you know, the eta prime potential, and essentially, you know, how is the U1 problem of QCD solved? Okay. So let's just go back first to ordinary QCD. So for now, let's put supersymmetry aside and just explain to you what is it that people usually say about the U1 problem in QCD. Yes, and then I will explain what is it that you see in the supersymmetric version of QCD. Okay, so again, so of course the U1 problem is the question, you know, that if you add F flavors, yes, then naively you have a UF cross UF global symmetry, and UF cross UF is broken to UF vector, yes, so there should be F squared Goldstone bosons, but you only see F squared minus 1, yes. So for example, in QCD you only see 8 Goldstone bosons rather than seeing 9. The ninth one would be this infamous eta prime. Yeah, so this is what used to be called the U1 problem in the 1960s. And then, of course, you know, people in the 70s came and said, oh, it's not really a problem, you know, there are anomalies, the U1 axial is anomalous, there will be instanton effects, and the initial reaction was instanton effects give mass to eta prime, yes? And at least on the phenomenologist side, you know, this is what we usually repeat. There are instantons, instanton effects give rise to the eta prime mass, and, you know, we shouldn't worry about this at all. So let's see how that would be reflected in the chiral Lagrangian. Yes, so in the chiral Lagrangian, then, so this is the usual chiral Lagrangian of QCD. Yes, so the U would be the Goldstone boson matrix, whose phase is the eta prime. Yes, so this would be one where you have the pion, the kaon, and the eta in the exponential, and the overall phase of U would be the eta prime. Yeah, so it contains all the 9 Goldstone bosons. And then here you have the explicit breaking terms due to the quark masses in normal QCD. And then what you would normally say is, okay, so there's an instanton effect. The instanton effect breaks the U1 symmetry explicitly. So I'm going to have to add an extra term to my Lagrangian that only transforms under the U1 axial. So the determinant U is an excellent candidate for that, because the determinant U is invariant under the SU3 left cross SU3 right global symmetries, but it's not invariant under the U1 axial symmetry. Yes. And then what you would do is you would add a coefficient to it that is proportional to the theta angle of the theory. Yes. And that would tell you that, okay, this is proportional to the theta angle because it's an instanton effect. Yes, the instanton effects always come with e to the I theta. Yes, and in terms of eta prime, yes, the actual potential that you're adding in here is going to be proportional to this combination of theta and eta prime. Yes. So again, it's an instanton effect because it's proportional to e to the I theta. It would give you a mass to the eta prime that is proportional to lambda, and it's very nicely consistent with the usual Spurian analysis for the axial U1, because what you know is that so the eta prime would be the Goldstone boson of the axial U1 if the U1 was, you know, if this was a true unbroken symmetry. So the eta prime under an axial U1 actually shifts. If I do an axial U1 rotation, the eta prime shifts, yes, because this will be the Goldstone boson of that broken U1. But you also know that if you do an anomalous rotation, yes, then the theta angle effectively is going to be shifted. Yes, so you can restore that shift by pretending that the theta also transforms under this U1 transformation. So this is going to tell you that anything can only depend on the combination that I have shown before here, yes, can only depend on the combination of theta minus f times eta prime. Oops. Sorry. Yes. Okay, and then what you can do is you can go ahead and integrate out the eta prime from the previous Lagrangian that I showed you. Yes, from this Lagrangian. Yes, so now you can integrate out the eta prime from here. Yes, and then you're going to get essentially the usual Lagrangian that you're going to see, you know, in all the textbooks that are trying to describe for example, axion masses or the theta dependence of the QCD Lagrangian. Okay, so if you also integrate out the pions, then you just get the theta dependence of the vacuum energy of the theory. Yeah, so this is the usual vacuum energy, and this is what is usually used for axion physics. So people say, oh, if you have an actual true axion in the theory, yes, that means that you have an additional anomalous U1 symmetry, U1 axial symmetry, PQ symmetry, under which the axion shifts and the theta parameter also shifts, yes, then you know that it has to be a combination now of theta plus A times n, yes, and then this is the effective Lagrangian that you get. Very good. And if you're interested, you know, how to get the axial mass, of course, the one thing you do is then you just integrate out the pions, yes, from this, and you get the usual formula. Okay, very good. So that's the story that, you know, the phenomenologists usually say, but when I talk to my formal friends, they say, oh, no. And that's actually not the right thing, yes. And in fact, so that's sort of the story that, you know, was propagated, you know, after Tuft's original paper of how instanton solved the U1 problem, yes. But, you know, Witten already, like, you know, a year or two after Tuft's paper, realized that that's not quite the right story. It's pretty close, but not quite the right story. And the way he realized it is he looked at the Lagrangian limit of QCD. And what he realized is that actually, you know, if you go to the Lagrangian limit, what happens to the anomaly is that because what you're supposed to do is you're supposed to hold not the coupling, but the Tuft coupling fixed. Actually, in the Lagrangian limit, the anomaly is a 1 over n effect. Yes. So what actually happens in the Lagrangian limit, the anomaly goes to 0. Yes. So that means that actually the eta prime mass should be vanishing in the limit when n goes to infinity. Okay. Now, if you look at my previous naive Lagrangian that I added to the chiral Lagrangian, that actually doesn't vanish for Lagrangian. Yes, you can check, you know, I mean, you have to take into account Lagrangian scalings of lambda and f, but you can check, you can take my word for it, you know, it doesn't, you know, it actually doesn't vanish. Okay, it is always of order lambda. Okay, and again, you know, I didn't discover this, unfortunately. Witten discovered this in 1978. So, and then Veneziano and others. So what he said is that actually that means that so the eta prime mass should go like 1 over n. And in fact, you know, he was able to identify just using Lagrangian counting, you know, what the theta dependence of the vacuum energy of QCD should be. And you know, he identified that. And from there, you know, also knowing what the relation, you know, how you get from the theory with a theta to a theory with an eta prime, he was also able to verify that this is indeed the right behavior for the eta prime mass. Yes. So that means that actually, you know, the kind of term that we added to the Lagrangian before, which was just e to the minus I theta times that cube, is not the right one. It should have some really weird form. It should have, like, for example, one possible way to take this effect into account is to take the nth root of that term. Okay. Now, that sounds a little crazy. You know, it gives you the right answer in terms of, you know, how eta prime behaves and what the theta dependence of the vacuum energy is, but it looks a little crazy as, you know, it's A is not analytic, yes. And if you write it in terms of the theta angle, you see the kind of theory you're now going to get now, because you have a 1 over nth root with a theory where instead of having a cosine of theta, you have a cosine of theta over n. Okay, so it's actually not 2 pi periodic in theta. Okay, so now that can't be the final story either, because you know that physics in the end must be 2 pi periodic. So that's also something that Witten already knew in his first paper in 78. He looked at it and said, okay, the solution of this must be that this has to be a theory that has several branches. Okay, and what happens is as you start changing theta by 2 pi, yes, and if you don't go back to the same value, yes, then actually you are jumping from one branch to the other branch. Okay, so if you have a potential of this sort where you have cosine theta over n, yes, then you can also add the plus 2 pi k there, yes, and that k is going to number the branches of the theory. Yes, and you can jump from one branch to the other branch. So the kind of potential you have is that you have these various branches and their periodicity is bigger than 2 pi. Yes, but if you look at the lower envelope of the theory, which is the true vacuum of the theory, yes, that is actually going to be 2 pi periodic. Yes, because essentially as you move by 2 pi, you jump over from one branch to the other branch. Okay, so this is actually how QCD is actually supposed to behave. Okay, so I want to stress. So far, I talked about ordinary QCD. This is our story of QCD. Yes, I didn't, it's not my usual BSM stuff where I make up something. This is how QCD is supposed to behave. Okay, so the question that we are trying to understand then is, check this picture in the supersymmetric case, and that's something that also Michael Dine was, of course, was also interested. They didn't use AMSB. They could just do the kind of thing that Massimo will just add any self-breaking term, and in some number of flavors, this is actually going to be reliable. So they were able to do this, and so it's very nice because now we can just explicitly go through our theory and check what happens to the eta prime potential. Okay, so first we looked at the theory where the number of flavors is less than the number of colors and add some quark masses, yes, and we identified the meson vests as usual for the AMSB type of story, and then what we were really interested in is what happens to the phase of this meson matrix, because that is what is going to be identified with the pseudo-Goldstone boson matrix and identified with the eta prime. Okay, so here we have to be really careful to keep the phase everywhere. Yes, so we are usually a little let's assume everything. Here you can't assume it's real. You want to keep the phase. Okay, so we were able to get a simple form of the actual Lagrangian and get what the eta prime potential is. Again, there's nothing really hard at this point here. Yes, we have a Lagrangian. You just want to make the right substitutions in it and then identify what the potential for the eta prime is. Yes, so we found something interesting here. Yes, so we do get the kind of branch structure that was prescribed by Witten, but not exactly that kind of structure. So in pure QCD, when the number of flavor goes to 0, we got exactly Witten's answer. Yes, so you get theta over n essentially, and the branch structure as he predicted in 1978 or whenever. If you add a small number of flavors and take the number of flavors, the number of colors much larger than the number of flavors, the story is still exactly just like predicted from Witten and also by Michael Dine et al. Okay.
But for f equal to 0, well, the mesons come from the EKG. No?
So for f equals 0, yes, there's no mesons. Yes. So then there's only a theta. There's no eta prime. Yes. So there's only a theta dependence. Yes. So we get that. That's this is what Witten said, that you will get this n squared times the function of theta over n or something like that.
But
It's just the theta dependence of the energy.
for eta, if f equal to 0, can you check it? I mean, apply your story to the Veneziano-Yankee
Right.
Lagrangian.
Well, so we certainly get the Witten-Veneziano relation, yes. And then the question is, yes, so I'm going to show you where does it come from, yes. So I'm going to explain that where does it come from, yes. But let me just first show you the answer. So one interesting situation that we found was that when the number of flavors is not negligible to the number of colors, then the situation was actually very different. So for example, when F was equal to n-1 and both are very large, then you are finding no branch structure for the theory. Okay. And the eta prime mass actually doesn't go to 0 in that case. Okay, you can check what the limiting case of the eta prime mass is. So the large F, large N is qualitatively different from the large N fixed F case. Okay. So what are the things that we are learning? Yes. So first of all, when N minus F is bigger than 1, it's not going to be an instanton effect. The eta prime potential is not an instanton effect, just like it's not in QCD either. Yes. In QCD, it's unknown what the origin of that eta prime potential is. It's whatever causes confinement. That unknown mechanism that causes confinement is the same mechanism that causes the eta prime potential. For the supersymmetric case, we know what the origin is, and it's just like Massimo was saying, it's gaugino condensation. Yes. So of course, it's great that we can identify it. It's not so great that it's a sort of inherently supersymmetric thing. Yes. I mean, what we are saying is that SUSY is broken, but of course, our M is not very large. Yes. So the gauginos are not lifted way out of the theory. Yes. They are still part of the low energy strongly coupled Lagrangian. And in fact, in this case, it's these gaugino condensates that is causing confinement and the eta prime potential. And so when F is equal to n-1, this is actually going to be an instanton effect. There will be no branches in the theory. Okay. And of course, in that case, the eta prime mass doesn't vanish, but the anomaly also doesn't vanish. So there's no contradiction there, yes, because the anomaly had an F over N coefficient in front, yes, and we said, oh, N goes to 0, N goes to infinity. But if F over N is held fixed, then of course the anomaly doesn't go to 0. Okay, now which one is QCD? Well, unfortunately, QCD has F equals N. So does it have branches or not? So we did identify, then you have to go, at least in the supersymmetric versions, to these special cases. And so we looked at it again. I don't want to go through all the details because, I mean, it's the analysis has a little bit more different technical things, but it turns out in that case, there are no branches, at least in the supersymmetric version. It looks like an instanton effect. And the same thing happens when F equals n+1. Okay, very good. Now let me just maybe outline quickly the two other interesting directions. One of them is the spontaneous CP violation in QCD, and in our case, in the supersymmetric version of QCD. Now, what is that? Why have you never heard about this? Well, it turns out that, of course, that trace GG dual is CP odd, yes? So this is what we usually say, the theta term breaks CP, that's the strong CP problem. However, there is one very special point, yes, and theta is equal to pi, yes? So then the effect of CP, yes, because this is CP odd, yes, then you have trace GG dual, it picks up a sign. So theta equals pi goes to theta equals minus pi, yes? But the theory should be invariant under 2 pi shifts. So this theory, this term, where the coefficient of the trace GG dual is exactly pi, doesn't actually explicitly break CP. Okay. However, it could spontaneously break it. Okay. And in ordinary QCD, it may, and in fact, Seiberg, Zohar, and Franz, have been writing papers about this using these techniques of these generalized symmetries, and they argued that in ordinary QCD, in fact, CP will be spontaneously broken. Okay, so the claim is that for 0 flavors, it's spontaneously broken, both for large N and for finite N. And when F is greater than 1 and all masses are equal, CP will be spontaneously broken. And for F equals 1, that's the most interesting case, there should be a critical mass at which there is a second order phase transition. Okay. So this is something that we can just go ahead and very explicitly check for our supersymmetric theories. And we are going to reproduce exactly the story that that these guys outlined a few years ago for the ordinary case. Okay, so again, what we are doing is, we are going to go to the F equals 1 case because that's the most interesting one. That's where you are supposed to be seeing the second order phase transition and find the critical mass. Okay, so we just
in terms of the QC application, one might have naively thought F equals 2 would be good because you have.
Right,
up
so
and
we
down.
are gonna show
you're
F
saying-
equals 2 also. We are gonna show but the F equals 1 is that it's gonna explain what is really happening.
Okay,
And then the F equals 2 is gonna be very easy to understand then, once you understand the F equals 1. Okay. So here, again, we just have our potential. This is essentially the same Affleck-Dine-Seiberg superpotential with AMSB added on. So this is our effective potential for the meson. Yes. And then the question is the meson valve going to be real or imaginary? Yes, that's what is. So what we are really interested in is, what is the phase of this meson valve? Okay, so we go ahead, minimize this potential, and it turns out that for small number of colors, you can actually analytically find the minimum. Once the number of colors is bigger than 3, we couldn't do it analytically anymore, but you can take the larger limit and you can also do it numerically. And you are finding actually the critical mass, just like predicted by Zohar and Seiberg and company. It depends on the number of colors. So we have a larger limit. And here is the phase structure. So you can see here what happens to the delta, the phase of the meson matrix. In the minimum, you can see that there's a critical value. The critical value depends on the number of colors. So the bigger the number of colors, the smaller the critical value of the mass is going to be. And once you reach the critical value of the mass, you get this bifurcation. Yes, that's the signal for spontaneous symmetry breaking. Okay, so also you can see explicitly what happens, for example, to the potential of the eta prime. Yes, because essentially the eta prime is going to be the object. Yes, that is going to be exactly massless. It's essentially the value of the eta prime that is telling you whether or not you have a spontaneous symmetry breaking. But as you go through the critical value, you see the potential completely flattens out. At that critical mass, the eta prime is actually exactly massless at the minimum, and after that, you're going to have these two different minima for the potential. Okay, so here's the phase structure. Yes, so this is theta equals pi. Yeah, so theta equals pi. Yeah, so you can think of that as having a negative quark mass in the theory. Yeah, so this is the theta equals pi. The theta equals 0. Yes, that would be the continuation over here. Yes, there's no CP violation over here. As soon as you reach the critical value, then you're going to get a spontaneous CP violation, and there will be a domain Volt theory that you can actually calculate here, and you get a second order phase transition with a massless eta prime over here. Okay, now here is the question about the higher number of flavors. So now that's actually relatively easy to understand. Yes? So it turns out that so there are two limiting cases. Yes, I can take the two flavors, and if one quark mass is much bigger than the other, yes, then essentially it's going to be a one flavor theory. Yes. So if I take the ratio of the quark masses to be not equal to 1, yes, if I'm going away from the diagonal somewhere here, yes, and I'm going in this direction, yes, then I'm supposed to see a phase transition, because essentially one quark mass is much bigger than the other, so there's got to be a critical mass. So if I go in this direction, yes, then you are supposed to always see a phase transition. So the fact that you have sort of this box-like asymptotic structure, yes, that is sort of baked into the theory. The question is, what happens down here, yes? And so it's really interesting, if the quark masses are exactly equal to each other, yes, then CP is going to be always broken all the way down to, almost the origin. Of course, at the origin, it should be unbroken, yes, because you have a massless fermion in the theory. Yes, and now where does QCD lie? So that's the mass ratio. Yes, this is the normal mass ratio. So we don't really know exactly, which that the up to down quark masses. So we don't exactly know. It could be either in or out. Very good. And you can check again. Depending on how you cross the phase boundary. If you cross it here, your eta prime mass becomes massless only once. Here it goes through 0 twice. Okay, so there are the 2 zeros here, 1 0, 2 0. Okay, very good. So this is fine. No, let me just say just a few minutes about because this is the thing that we are doing now, and you're getting quite excited about this. Is now we are thinking about the up quark mass generation in these QCD-like theories. So the important thing is that we have essentially the chiral Lagrangian. Yes, you just have to do a little bit more calculation, and we essentially have even the higher order terms in the chiral Lagrangian. And it doesn't matter, I'm not going to show you the details, but so what we are interested in is deriving the chiral Lagrangian. There is it, the chiral Lagrangian to higher order in the quark masses and to higher order in the derivatives. And again, we have the full thing. So, it's just a little more calculation to make sure that we have a linearly realized theory, and we have to map it onto this non-linearly realized chiral Lagrangian that people are usually interested in. Okay, so we can actually go ahead and get all of these other operators. So you remember, for the leading chiral Lagrangian is just the kinetic term plus the quark masses. But after at higher order, you can have more derivatives, or you can higher terms in the quark masses. Now, so you can go ahead and do this, and I'm not going to show you. You just integrate out a bunch of fields. Yes, I'm not going to show you the specific thing, but we have the explicit results here for all of these L1 to LA. Okay, very good. So now, why is this interesting? Why should you care besides saying, oh, it's great fun? Yes. Now, the story about the strong CP problem is that there is one simplest solution, which is that the up quark could possibly be massless. Okay, so now the lattice people keep telling us, well, that's disfavored, that's not the ratio we see. However, it turns out that it's actually not that easy to directly read off what the up quark mass is from the lattice. So Kitano wrote a very nice paper, and I haven't seen too much from the lattice people trying to respond to him, where he was saying that the true non-perturbative effects are really hard to disentangle from the lattice. And he did himself a lattice calculation, and he said he couldn't decide whether it's disfavored or not. Okay, but the upshot is that the quark mass is not multiplicatively renormalized, so it's not enough to say that at one particular point you're saying that the M-up is not equal to 0, because instanton effects are going to give you an additive renormalization. Okay, and so there's this particular operator that is generated by instantons, and so that's something that Banks, Near, and Seibers are looking at in the law. All this, it's a little complicated story. I don't want to get into the details. This operator that turns out is not independent of all the others. The upshot is, we can go ahead and calculate all of this. Yes, so we can identify what the dynamical contribution to the up quark masses in this particular theories. And what we are finding is that actually, so there's a particular expression. Yes, this of course depends on the strange mass, depends on the strong coupling scale, and the SUSY breaking scale. Of course, the SUSY breaking scale is small. Yes, this is a very large thing. Yes, but the question is, could we be able to extrapolate this to the limit when m is of the order of lambda? Yes. So that, of course, is outside the region of our approximations. But what we do find is that if we close our eyes, take the formula that we derive for small m and take m equal to lambda, actually, the dynamically generated quark mass is pretty sizable. Okay, so it could even possibly account for all of the observed upmass. So
There's no axion. I'm just kidding.
I did not say that. I said I close my eyes.
He doesn't need an X.
I'm just saying that, this is something that to me is not completely resolved within QCD. And, certainly, these kind of theories seem to suggest that it could be actually pretty big. So it's not totally obvious to me that I should discard the M-up equals 0
But if
solution.
M is actually, to be safe, an order of magnitude larger than lambda, right? Then that contribution.
Wait, why?
Well, the
Just repeat
contribution
it
was like
louder. I
one of the-
don't think I heard.
The contribution goes like 1 over m square, and to be safe, you want this.
Well, not really. Yes, no. I mean, but no, because what you're expecting is that once you hit m equals lambda, yes, then it's going to saturate. Yes. So because right,
Give me the
It's like
time equals lambda.
QCD
yes,
screens.
exactly,
that
so,
not
right,
perturb-
right.
there you go.
yeah, so I think at least for all the other things, we always close our eyes and check what happens, yes. So you get usually the QCD answers when you set m equals lambda. So you don't say that, oh, by after that, it's going to be really big, if it's m over lambda. Yes, m over lambda usually gives you the right scalings for QCD. All right, very good. Sorry, I already abused your time, so let me just summarize. Yes, so again, what I was arguing is that you can get a lot of fun by looking at these SUSY theories and trying to see what happens to confinement and QCD-like physics there. In particular, this AMSB, this anomaly-mediated version of supersymmetry breaking, is UV insensitive and it produces a QCD-like phase structure. And I went through three particularly, to me, interesting dynamical effects that are sort of not completely easy to fully explain within QCD, the eta prime potential, the phase structure of QCD at theta equals pi, and then this dynamical up quark generation, and you're finding interesting things. And now exactly what should I conclude about this? I don't know. I mean, it's in these theories, I'm pretty sure this is the right answer, but should I conclude anything about QCD? And who knows? All right, thank you.
Could you go back one slide
Yes.
so we can ponder that
Right.
while you,
Right,
no, 2 slides.
sorry. No, so this is the wrong direction. Let's back up. Yes, right. Right. So again, here, I just shoved in brute force, some strange quark mass. I took, lambda and m to be 200 MeV and see, what kind of dynamical mass ratios do I get? And so this is actually almost the right one.
Yeah.
But what is the Gaussian mass at with this m? Because that you want.
So the Gaussian mass you would expect is going to be hopefully of the order of lambda, yes.
So you don't gain when m is equal to lambda, all these other factors, betas, etc., are order 1.
Well, again, so of course if you still think that you don't expect that the perturbative answers are the right ones, yes. So yeah.
No, but I mean, because you had a formula for the Gaussian mass.
Right,
so
assuming the couplings are small, yes.
assuming that the coupling is small,
One
then the
loop,
Gaussian mass
one
is of
loop.
the order of lambda.
G squared over it's G squared over 16 pi squared times m.
So
Yes.
you put at m equal 200 MeV, the Gaussian could be very
It
still light.
could be if the perturbative answer is the right one, yes. I mean, the assumption is that that's not going to be the right one, but yeah. Again, I don't know, I think, you should take it with a big grain of salt. Yes, it's just a fun thing, I think this you should trust. In the regime where m is much smaller than lambda, but it's not for a theory that you are particularly interested. Now, do I really extrapolate to QCD? Hitoshi always says yes, but
Could you go back one more slide? I
Yes.
think that's where you tried to compare the ladder. No,
oh,
sorry.
sorry, I'm going
right,
in
okay.
the wrong direction. Yes, right.
I think I meant. I
Maybe
feel like it was
there
a
are
little
lots of
further
slides
back.
here.
Maybe the one with Kitano.
Kitano, this one.
I thought there was, oh yeah, maybe
Yeah.
it was right, the katana. I was dreaming. The next one, sorry. I
Right.
think I was really wondering. I thought there was a slide where you were trying to compare to some lattice observation, and I wish.
No, I don't have that particular. All I said is just this, that in around 2010, the lattice people said, "Oh, M up equals 0 is excluded." Yes, they just said
I
it's
was just-
excluded. Yes,
I-
and
I-
then there was this paper that said, "Well, really, you have to look at the topological susceptibility. It's not enough to just calculate the M up directly." And I'm not really an expert on this, so I can't take. I'm definitely going to send my paper to Kitano before I publish it to make sure that I don't see anything stupid about the literature. But I think I talked to him a few months ago, and he still seemed that it's not, in his mind, it's not totally settled.
But in the formulas that you have for small m,
Yes.
when m is equal to 0, what you get, that the down becomes massless, or it's just misreading the formula? Yes. Because when n goes to 0, right?
I have to think about how to interpret this, this is something we were doing yesterday, so. I just wanted to have something for this talk that where I can plug in numbers. It's actually, I'm not, reading off exactly what the dynamical quark mass is not totally obvious to me, so I'm still a little, hesitant about these formulae. Because in terms of this particular operator, it's clear this is what Seiberg and Banks and company were saying, but that's not quite the operator that we have. We have like 4 other operators which are linear combinations, so
Could you directly look at M5?
right. So that so the way I was defining this M up over M down mass ratio is the following. We have a mass formula for M pi in terms of M up and M down. Yes, the leading thing. Yes. Now I'm going to set M up to 0. Keep the down contribution, plus add the contribution from the higher order terms, and identify
Equate that to M5.
exactly to M up. Exactly. To whatever shows up to M up in the pion mass.
Oh, in the
So there's an expression in the pion mass, there's B0 over F pi times M up plus M down or something like that. Yes. And I'm going to set M up to 0 in that. Look
Keep
at the
all the
higher
rest
order
of the term,
contribution,
right.
and then identify that with the effective up mass.
Right.
That's what I'm trying to do.
But it'd be in a way more direct just to say, well, let me just look at all the QCD observables like M pi,
Right,
M
right.
eta.
Yeah, so really you should do a full fit.
I just think that would be in a way that, who cares who knows what we actually mean by M up?
Right.
Sort of in this regime.
So I
why
mean,
not just look at
so
all the
we
QCD
wanted,
observables?
that was our original thing, let's just do a full fit, but then, it would be a lot of work, we would have to understand in detail, exactly what the error bars are, which, we are not experts on a theory where, it's way outside the regime. So to me, it's more useful to sort of give an intuitive picture. This is the order of magnitude of the correction. And
Well, we can talk offline,
Yes.
let other people ask questions.
With the n that you take, like it's kind of a question I guess Glennis asked a little bit earlier, but with respect to the number of flavors, right? So up and down are obviously very like compared to the QCD scale, but strange is close. So like is n is 2 or 3, like, and it seems does that change it by order of
well,
one
strange is not well.
or 100 MeV, right?
Right, but but the other thing is that strange, the quark masses are holomorphic, so there's no problem
Oh.
with taking. I could even take the quark masses bigger than there's no real problem with it's the SUSY breaking scale.
But
That's the one that is non-holomorphic that I cannot.
so
I could, in fact, one thing that we are thinking about is including a charm quark. And so I didn't show you this, but you're interested in that we include a heavy quark and see what happens there. And because again, there's no problem with having the quark mass is large
compared to lambda
compared to lambda. It's
Right,
the
but the
SUSY breaking scale that you can't
right?
take big.
And you took that to be 200 MeV in this example, but you were also saying for Massimo, it doesn't matter if you take it higher, the results should still be the same at the ratio.
Well, I mean, numerically, I think it will. All this stuff.
That's very,
Maybe
some sort of spontaneous breaking.
You turn off Zoom.
Is that better?
How did that happen?
I think maybe David unmuted his laptop. Is that what happened?
No, I think Chaba's
But it's on my
speaker
laptop, but
came unmuted. I have no idea.
probably maybe with the.
One there,
I don't
maybe.
know. Anyway, it's
Could you put this exact model on the lattice and study this lambda equals m behavior? Maybe try to get some understanding of whether the perturbative naive intuition holds or.
probably, but maybe the lattice people would rather do
It's
ordinary.
like a very nice idea, doesn't it? It's a regulator for you,
Right.
and so they would.
So the question is,
Might-
does this make it easier for them?
Yeah, it might
I
very
guess
well.
so. So if the answer is yes, but I thought they had hard time just putting Suzy on the lattice. To begin with, so.
There are a lot of firms.
So it's a lot of fermions,
Genomics
exactly,
and.
chiral
quarks,
fermions.
right?
So I thought, they are already struggling putting any supersymmetry on the lattice, but
Well, the trouble was the fermion problem, but, since you're gonna have a mass, since you're breaking it, you've
Right.
got a massive gaugino, maybe. That's very interesting.
yeah. So
Are you gonna be here
I'm
longer?
here today, actually tomorrow I'm going to Stony Brook, on Friday and back again, so I'll be here all this Friday.
Maybe I'll catch you
Yeah,
later. I have
Yeah,
to
absolutely.
do a Zoom
I'll be here
now,
on
but
Friday. Yes.
I may not be here on Friday, but maybe I can catch you later.
Yeah, I'll be here all day today also.
Well, if you have more questions, maybe we should thank Csaba first and then ask him after. Also, like, Thursday and Friday, some of us go to CCA. And we can get you also, I guess, access to like. come
So
sometime.
nobody will be here today.
I don't know, Josh sometimes comes.
I'll be here
Friday.
Friday.
Okay,
Yeah.
I'll be here.
So, but yeah, okay.
Also, actually, Shubik said that he's coming back and he's going,